The goal of this project is to build an intelligent basketball return machine which can recognize a player, track their location, and dispense a ball when requested. The ball will be 6 inches in diameter and must be launched at least 10 feet using friction wheels spinning at 1300 RPM. The launching mechanism will rotate using one 7.4 volt servo. Computer vision is implemented to recognize the call for ball gesture within 10 feet and 60 degrees point of view. To launch a basketball, the upper wheel rotates towards the back and serves the ball to the front wheel, which is rotating in the forward direction. Additionally, the friction wheels are spaced together slightly closer than the diameter of the ball. This creates a force vector perpendicular to the wheels and launches the ball forward. Powering the friction wheels is a 5203 series yellow jacket planetary gear motor capable of spinning at 1600 RPM. Our wheels only spin at 1300 RPM. The wheels themselves are 7-inch diameter polyurethane scooter wheels and receive power from the motor via bevel gears on the upper and lower axles. Controlling both the 12-volt DC planetary gear motors is a Cytron dual motor controller. This controller receives PWM and direction inputs from the Raspberry Pi 5, which it uses to regulate voltage from the 12-volt battery to the DC motors powering the friction wheels. Additionally, the servo must be able to rotate at least 30 degrees in either direction to track the player within the camera's field of view. To enable rotation, a 25 kilogram per centimeter servo is used. The servo is controlled using a hardware PWM signal from the Pi, which dictates the launcher position. The servo is housed within a rotation kit, which reduces the load on the servo shaft. The servo receives inputs from the camera, which is mounted on the front of the system. The camera uses OpenCV and a holistic model to recognize players' bodies and then focus in on their hands. The angle from the center of the camera is calculated and the servo is rotated to face the player. If a gesture is detected, a ball will be dispensed and the fade-in sequence will begin for the friction wheels. Once a gesture is detected, the ball dispenser, shown on the left, will rotate 1/3 of a revolution and allow a basketball to slide through the pass and down the ramp to the friction wheels. In order to keep track of score and accuracy percentage, we tapped into the IR sensor built in to the door hanging basketball hoop. This sensor feeds to an interrupt on the Raspberry Pi 5, which is used in conjunction with the amount of balls dispensed to calculate accuracy. The accuracy and other statistics, such as the shots made and time passed, are displayed on a graphical user interface on the front of the system. The wiring diagram is shown below. A single 12-volt battery is used to power both of the friction wheel motors, the dispensing motor, and the servo motor. All DC motors receive PWM signals from the Raspberry Pi, and the servo motor receives a hardware PWM signal from the Raspberry Pi. The camera and display communicate data with the Raspberry Pi. Taking a look at the flowchart and system logic, when the game begins, the camera is activated as well as the IR sensor. Next, the camera scans for a hand, and if one is detected in a new location, the base servo is rotated to the desired position. Then, a user gesture is scanned for. If the gesture is detected, a fade-in sequence for the friction wheels begins, the ball is dispensed, the wheels fade out, and the system returns to scanning for the hand. If a gesture is not detected, the system returns to scanning for a user's hand. When end round is pressed, the system shuts down.
Yeah, so for demo one, we began working with building up our model, trying to figure out what we want to use for hand gesture recognition. We didn't want to make the whole semester of building a completely new model. We were able to get started on implementing that, especially through Google's Media Pipe, which is where we got our hand recognition from.
So for demo one, we didn't want to overcomplicate the graphical user interface or the GUI, so of course we just had a simple start game, and we had a little bit of confetti just for something to show Raza, but other than that, we don't want to overcomplicate the system.
So prior to demo one, really, that's when most of our planning took place for just the overall system architecture, and then going more into depth about actually what we were going to attempt to do. However, that first order was delayed several weeks.
For demo one, we honestly didn't get too much. The parts being delayed really slowed the start of our project, but looking back on it, having that time to dive deep into the servo and DC motor control on the Pi 5 really came back to help us with issues that we ran into down the line with the fully integrated system. I remember getting a text from Mike late one night, hey, all of our parts are in rigs, build day tomorrow. I was super excited. The whole team was there, built the servo base, the launcher assembly, the friction wheels, interfaced the new motors, and at the end of the day, we walked away with a rotating launcher assembly.
Demo 2, the servos finally came in, and the guys were quick on it with figuring out the servo, the code for that as well. So it's very easy to implement that with my model, work on hand tracking, and then also getting an angle to input from my model to the servo so it would be able to turn and track those hands.
The launcher assembly had been built, and we were able to interface that with the servo, and we were able to spin up, spin down the friction wheels to launch a ball. However, we lacked a big component in this build, which was stability. And so I spent the weeks leading up to our milestone 2 demonstration basically thinking of ways to improve the stability of our system, which is when I thought of the box idea. So basically the box houses the servo and pretty much every other component relevant to our project. You see, like, I'm standing over here with both my hands over here and it's pointed straight ahead.
Okay, yeah, so to troubleshoot the servos, first we had to diagnose the issue of whether our PWM signal was off. So our Raspberry Pi acts more closely to a computer than a microcontroller. And so what I mean by this is whenever we're running a software PWM, other interrupts are happening. The Raspberry Pi is handling other instructions during the process of generating this PWM signal. After that, we look towards, what angle were we getting from the camera, ensuring that that was accurate. We needed an accurate FOV, an accurate resolution to calculate the midpoint of the player in his hands. And then that issue, we got it to rotate accurately. The ramp was the elephant in the room, and Mike really took it upon himself to address that.
So the ramp assembly was a very, very challenging part of this project. It took very many design iterations for figuring out how to actually attach a ramp to the rotating launching assembly, and then also dealing with how to dispense one ball at a time, and taking to the notebook, sketching out different design ideas, and then transposing that into SolidWorks, where I was able to 3D model basic design concepts and then improve on those over time.
So I was also in charge of our wires and soldering for the entire project. Once we got near the end of the project, we had probably close to 40 wires that were made using breadboard wires. So I was in charge of soldering wires, designing circuits, and this also went to a small task I had with John
with figuring out how to implement the IR sensor for the basketball goal.
Of course, when integrating the board with the IR sensor, we did have a few problems. One of the major problems is that the board was getting too much voltage to the Pi. So of course we had to make a interrupt pin on the Pi along with a voltage divider, which allowed to go below 3.3 volts to read it as a high input for the Pi.
Definitely a great semester. I really enjoyed senior design too. I really wish we had it sooner, because to be able to do a project like this, think of it all by ourselves, implement it all by ourselves, it was a great experience.
So don't get me wrong, there were milestones along the way, trials, tribulations, obstacles, challenges, you name it, we encountered it throughout this project. But basically, from the first time we launched a ball to the first time rotating the servo to seeing parts fit together as planned, it was all just a very, very eye-opening experience.
Seeing it all come together, that was something special. After all the time that the team had put into it, all the days, all the nights in the lab, running into problems, roadblock after roadblock, change after change, finally seeing everyone's hard work pay off, everyone's section of the project come together in the final integration. It was really something.
I thought senior design 2 was an amazing experience. I had a great teammate and a great project. In very few classes do we actually integrate both components together, and so senior design had a great time doing that.
Learned a lot about what it takes to work with other people, schedule meetings on our own time, and just task things to certain people based on their strengths.
We wouldn't have been able to do it without each and every team member. Everybody excelled in their areas, helped when they needed help, and really just came together to make an absolutely fantastic senior design 2.